Okay, so from section 7.1, we're going to look at equivalent forms of exponential functions. And what we'll say from that is if we can say we can rewrite exponential functions by finding equivalent forms of the base. And this is where it's going to come in handy to know some of those exponentials that I was just talking about. So for example, we know that 2 cubed is 8. Okay. So if we have a function, say 8 to the power x, we can write an equivalent form of the base. We know that 8 is 2 cubed, so we can say, well, that's 2 cubed to the power x. And we can get an equivalent form of that function as 2 to the power 3x. Sort of idea. We can also apply equivalent exponentials to simplify an expression. Okay, so we can also do a similar thing to simplify an expression. So if we had, say, 16 squared times the square root of 32. Okay, well, 16 squared is a number we could work out. It's going to be a big number. I'm really not liking doing the square root of 32 though. Okay, is there anything you notice about these two numbers? Anything you know? Okay, if we go through, we should notice that 16 and 32 are both 2 to the power. Okay, so what is 16? That is 2 to the power. Okay, 16 is 2 to the power 4. What's 32? 2 to the power 5. Okay, and we can rewrite that as 2 to the power 4 squared times the square root of 2 to the power 5. Now we could take that square root and turn that into a fraction. So we can say that's 2 to the power 5, 1/2. And we could still do 2 to the power 4 squared. Okay. Well, right here, these look like power of power rules from kind of way back. So that'd be 2 to the power 2 times 4 times 2 to the power 5 times 1/2. Well, 2 times 4 is 8, so that's 2 to the power 8 times 2 to the power 2.5 if we want. You keep it as a fraction if you want to as well. Now, how can we simplify these two? We have two things multiplied together that are the same base. What happens to our exponents? We add them. The base stays the same and we add. So we're going to get 2 to the power 10.5. If you kept that as a fraction, you would have had 2 to the power 21 over 2. All right, so we could also, right, we can do the same thing to solve an equation. Okay. And the equation we could solve, we could look to find out when 8 to the power x plus 2 equals 32 to the power x minus 1. Okay. So we can go through that same sort of thing. Let's look for equivalent forms of the base. So how could we make our base 8 and our base 32 have the same base? What can we do here? Okay. So if we notice that 8 is 2 to the power 3 and 32 is 2 to the power 5, we can rewrite this equation so that everything has base 2. So our left side is going to look like 2 cubed to the power x plus 2. Our right side is going to look like 2 to the power 5 to a bracket x minus 1. Okay? From here, we're going to use power of power rules, and we're going to multiply our exponents. So our exponents are going to be 2 to the power 3x plus 2 equals 2 to the power 5 x minus 1. Okay. What is going to be our next step? So if we wanted to expand, we could. So on our left side, we'll have 2 to the power 3x plus 6 equals 2 to the power 5x minus 5. What are we going to do from here? From this point, we can look at our expression and say, all right, well, we have an equation that's equal. We have a left side and a right side. Both sides have one term. Both sides have one term with base 2. So basically this is saying 2 to the power something equals 2 to the power something else. Okay, so from here, 2 to the power 3x plus 6 equals 2 to the power 5x minus 5. For those to be equal, 3x plus 6 has to equal 5x minus 5. Okay, if the exponents aren't equal, there's no way that 2 to those exponents are going to be equal. So we set those equal to each other, and now we can just solve them. Okay, we can bring those over. We will get 6 plus 5 equals 5x minus 3x. 5x minus 3x is 2x equals 11. Divide by 2, and we can leave that x equals 11 halves. Okay, that's a value for x that makes our original statement true.